Now we're going to talk about complex impedance. So impedance is a similar concept to resistance, and it relates the voltage and current relationship of a circuit element like a resistor, capacitor, or inductor. And it's a more general form of representing the voltage and current relationship. And in particular, for capacitors and inductors, the impedance is affected by the frequency and phase of the circuit elements and what they're exposed to. So, let's start with the easiest example, and that's that of resistors. So, resistors have an impedance, and it's basically the resistance, and that defines the voltage and current relationship. Now, since we're studying AC, our voltage and current, they're sinusoidal, and Ohm's law still applies. So we have, the phasor voltage of a resistor being equal to the resistance times the phasor current of the resistor. And in the time domain on the left, we have the representation: current going into a resistor, and then a voltage being developed across it. Okay, and the important thing to note is that the resistance is a real valued component, and its units are ohms. So it's exactly how we understood it from before, and let's just make sure we understand what it means in the context of AC circuits, and then we'll extrapolate to inductors and capacitors. Okay, so now if we put a sinusoidal current through a resistor, as expressed by the red graph here, then the voltage developed across that resistor will also be sinusoidal, and it will be in exactly the same phase as the current. Okay, so it won't be shifted. So that's fairly simple, and it's because the resistor is real valued that there's no phase shift between the voltage and current waveforms. So if we were to draw the phase diagram, we'd have to know the phase, and in this representation we have the current with some arbitrary phase shift of theta. So it's a positive value of theta, so the cosine waveform would shift to the left, as we know. So now the voltage waveform in green also shifts by theta the same amount. And if we were to represent that in phasor form, we would have the drawing as we have on the left. So we would have the two phasors, one of the current and one of the voltage, in line with each other at some arbitrary phase angle. Okay? So now, where it gets interesting is when we talk about so-called reactive components like inductors and capacitors. So let's start off with inductors. So now, inductors have a more complicated impedance, but they follow the same general format. So voltage is equal to the impedance, so we're calling the impedance of the inductor ZL. Okay, so that's ZL. And then we have that ZL multiplied by the phasor current to develop the phasor voltage of the inductor. Okay, and we see a representation on the left of the actual circuit. We have current flowing into the inductor and the voltage being developed across it. So now where it gets really interesting is the definition of the impedance for the inductor. So that works out to be J omega L. So that's a very interesting expression. So J that is our imaginary operator, so that's the square root of -1, okay? This W, that's omega, so that's the radiant frequency or the angular frequency. So it depends on the frequency of the stimulating source, what the impedance value will be. So, for example, if omega increases, then ZL would increase, wouldn't it? Okay, so that's very interesting. So it's frequency dependent. And then L is the parameter for the inductor, so like 10 millihenries or some sort of thing like that. And that's constant. Okay, so now the representation of J, so that's the imaginary operator, so it makes this entire term imaginary. Okay, and then, so if we were to plot it on the complex plane, it would be a vector pointing up, and that would be at 90 degrees. So it would be right on the positive imaginary axis. Okay, and it's also important to note that the impedance of the inductor is given in units of ohms, just like it is for resistance, because the dimensionality of this expression has to be obeyed in terms of the current times an impedance is going to give you a voltage. So now, what does this phase relationship mean in the circuit? Okay, let's take a look here. So we have what we've seen before. The phasor voltage is equal to the impedance of the inductor times the phasor current, okay? And then, what does that work out to? It works out to j omega L times the phasor current, okay? And then, in the end, what's happening is that current is being scaled by a value of the inductance times the frequency, and then the interesting bit is that it provides a phase shift of 90 degrees to the voltage waveform. Okay, so that's in mathematical terms. So what's actually happening in the circuit? So now, let's say we have our current waveform here. So that's the inductor current, and it's given at some phase angle, and because this inductor impedance is strictly an imaginary number with the interpretation that there's a phase shift of 90 degrees, what it does to the voltage is that it shifts the voltage 90 degrees compared to the current, and so this is the basic property of the inductor, shifting the voltage waveform from the current waveform. Okay, so let's look at it in terms of the phasor diagram just to make it a little bit more explicit. So now if we've given this current as defined, it's defined as having a phase. So in this case, it's minus theta. So the waveform, the cosine waveform, has shifted over to the right by minus theta. Okay, and then what is the effect on the voltage waveform? Well, the voltage waveform shifts over to the right by 90 degrees. Okay, and that's expressed over here, minus theta plus 90. Okay, so now in a phasor diagram, we can represent it like this. We're starting off with the current waveform. Okay, so it has a phase angle of minus theta. Okay, as we saw up here, and then we can write it in terms of the current magnitude and its phase, which is minus theta. So then, let's put that back. So then, if we're drawing the inductor voltage, that inductor voltage is going to be 90 degrees ahead of the current waveform, or the phasor for the current. Okay, so that's where we get this 90 from over here. Okay. And then the important thing to note is that the voltage leads current in an inductor by 90 degrees. So now, there are other formulations for for this relationship. It's basically Ohm's law, so we could write in terms of what's the current equal to. So this is just reordering the parts of that expression. Okay, so then we can say that if you take the voltage divided by the frequency and the inductance and provide a phase shift of minus 90 degrees, you get the current. So the current is going to be 90 degrees behind, or ahead, or no, behind of the voltage. Yeah, behind the voltage, okay, because the voltage leads the current in an inductor. Okay. So then there is, oh, and this is a very important expression. This is basically the definition for the impedance of the inductor, which is the inductor voltage, phasor voltage divided by the phasor current of the inductor. And then, as a memory aid, we can say, we can use this simple acronym ELI, and what that stands for is E stands for voltage or electromotive force, the L represents the inductor, and the I represents the current. And what this says is that voltage leads the current in an inductor. Okay, so that's something that could be useful to remember. And then just be clear that whenever you're drawing the current and voltage relationship for an inductor, that the inductor voltage will always be 90 degrees ahead of the inductor current. Okay? So then, let's see how capacitors behave, what the complex impedance of a capacitor is. Okay, so if we have the circuit arrangement like this, where we have the current flowing into a capacitor and then the voltage developed across the capacitor as Vc, then we can say that the phasor voltage of the capacitor is equal to the impedance of that capacitor times the phasor current. Okay, so, and the interesting part here is the phasor impedance, I beg your pardon, the capacitor impedance. So now, the capacitor impedance is equal to 1 over j omega c. Okay, so this is a different relationship than what we saw for inductance. So j again is the imaginary operator, square root of minus 1. Omega is the frequency of the stimulating source, and then c is the capacitor value, which will be a fixed value. In fact, the frequency will be fixed for us in our course, but it can vary. Okay. So then we can just operate and move the j up to the numerator, and it becomes minus j, and then that minus j represents a phase shift of minus 90 degrees, because the impedance is an imaginary number, and since it is minus j, that lies on the negative imaginary axis, so it's a phase shift of minus 90 degrees, okay? And then the impedance is given in units ohms, just like it is for inductors and just like it is for resistors. So what does it mean in terms of the relationships between voltage and current? Okay, so since the capacitor impedance, it has a negative imaginary value, it causes a phase shift for the current waveform to shift over compared to the voltage waveform. So it's basically been shifted 90 degrees, or vice versa. You can say that the voltage gets shifted 90 degrees in the negative direction. So it depends which is the stimulating source, actually, which waveform gets affected by the shift. But between them there's a shift of 90 degrees with the current being to the left of the voltage. Okay, so then let's just put in the phase of the waveforms and then show the phasor representation. So now what we have is that we have defined a phase, a positive phase on the current waveform of theta, which means that it's shifted a cosine wave to the left. Okay? And then accordingly we'll have the voltage waveform being shifted 90 degrees to the right compared to the current waveform, and that expression is theta minus 90 degrees. Okay? So then the phase diagram on the left represents the relationship between phase and current for the capacitor. So what we can see is that the current has been represented with a phase angle of theta, okay? And then we see that the voltage waveform has a phase angle of 90 degrees, of minus 90 degrees from the current phasor, okay? And the idea is that the difference between these two in terms of phase angle is minus 90 degrees. Okay? So that's the relationship between voltage and current for a capacitor. So what we have to do is keep in mind that the current leads the voltage in a capacitor by 90 degrees. Okay? So then we can just manipulate it in other ways. Instead of just VC being equal to the capacitor impedance times the capacitor current, the phasor current, then we can say that the phasor current is equal to the phasor voltage divided by the capacitor impedance. Okay? So we can just reformulate that expression in different ways. And then this is the expression for the capacitor impedance. So it's the phasor voltage divided by the phasor current. And then, as a memory aid, we can look at it in terms of ICE. So that's the current leads voltage in a capacitor. Okay? So let's do an example just to see how to operate with these definitions. Okay, so in this example, we want to find out what the inductor voltage is. And so we have a circuit that's being stimulated by some voltage source, okay, and this is the value of it. We have a sinusoidal voltage with amplitude of 10 and a omega of 100. Okay, so that's stimulating this circuit, causing current to flow. And in this circuit, we have, let's just fix this to make it a little bit easier. This is just an R. Okay, we have a resistor of value 10, and then we have a capacitor which has a complex impedance of ZC, and the capacitor value itself is 500 microfarads. And then we have an inductor, so that's represented by ZL, the impedance of the inductor, and the inductor has a value of 100 millihenries. Okay? And what we want to do is we want to find the voltage across the inductor, so the inductor voltage. So how are we going to do this? So what we're going to do first is we're going to recognize that this circuit is a voltage divider. So VL of T is the voltage across the inductor, and this is exactly in the same formulation as the voltage divider that we used for resistive circuits, and this exact same methodology for solving it applies, except now we have complex impedances and phasor voltages and currents. Okay, so we just have to translate. So as you can imagine, the equation for solving it looks very similar to what you would do using a resistive voltage divider. So the voltage in question, VL, is going to be equal to the impedance of this bottom element here divided by the impedance of the entire series branch. Okay? And then, of course, it's multiplied by the stimulating voltage, which is up here. Okay? So that's a very familiar formulation. So it's just that we're using Z's instead of R's. Okay? So then, let's determine the values. So for R, we know that it's 10 ohms. Okay? So now let's find ZC. So ZC, so that's the impedance of the capacitor, and the general formula is 1 over j omega c, which we saw earlier. So now we plug in the values. So we know that j is just the imaginary operator. Omega, it was given up here. So omega is 100. So we bring that down, and that's 100. Okay? And then C is the capacitor value, and that's it right here. So it's 500 microfarads. So that's what comes down here, 500 microfarads. And if we work that out, it works out to minus J20. And its units are ohms, so it's minus J20 ohms. Okay? And then, solving for the impedance of the inductor, we have J omega L. Okay, that's our general formula. So it's J times omega, which is a stimulating frequency, times L, which in this case it's 100 millihenries. So that's what drops down here. And then when we work that out, it becomes J10 or J10 ohms with the units. Okay. And then next we have to find out the phasor representation of the stimulating source. So we have to find for V. And the expression for that is 10 at an angle of 0 degrees. And where do we get that from? Well, 10, that is the amplitude. Okay, it's 10, that drops down, and there's no phase angle here, so there's no theta, right? It's equal to 0, so that's what we've got here. And so it's basically just 10, and its units are volts, so 10 volts. So that's the phasor voltage of the stimulating source. So now let's plug in the values into our equation. So this is the equation that we're working with. right? We've calculated all of the values. We've got ZL, R, ZC, and ZL in the voltage. So we just plug in the values. So ZL is J10, R is 10, and then we have ZC, which is minus J20, and we have ZL as J20, okay? And then we start simplifying, okay? Work it out. So then we just have J100 over 10 minus J10. So then we have to put it in a more convenient form, because we're eventually going to want to find the time domain function for the inductor voltage, okay? So then, to do that, we're going to start off with that representation. So I've just brought over the first equation, and then we're going to simplify it, okay? And so what we need to do is we need to make the denominator into a real number, okay? And to do that, we multiply by the complex conjugate of the denominator, which is what we're doing right here, okay? So that's the complex conjugate of the denominator, and all we have to do is flip the sign of the imaginary part, okay? So then, of course, we're multiplying by the complex conjugate over the complex conjugate, because that's the equivalent of multiplying by 1. So we're not changing the original equation. So then that works out to J1000 minus 1000 over 100 plus 100. Okay, great. And then we can continue to simplify it, and we want to get it into a standard form where we have the real part in the beginning, so minus 5, and then the imaginary part at the end, so plus J5. So that's the representation we want to get to. And then, so now we're going to have to convert this to a time domain representation. So what we're going to want to do now is convert this this phasor, this voltage phasor, into its polar form, and then from the polar form we can easily write the time domain expression. Okay, so in terms of rectangular coordinates, we have the phasor voltage expressed by what we see on the phasor diagram on the left, where we have the point right here at 5 on the plus 5 on the imaginary axis and minus 5 on the real axis. And then we need to make our calculation. So what we're going to do, we're going to convert this into polar form so that we can write the time domain expression. So then what we need to do is do the transformation into polar form. So then what we do is we calculate the magnitude of this vector, okay, and that's what's happening here. And that's simply the Pythagorean theorem, okay? And then we need to find the phase, okay? And we measure the phase from the positive real axis going counterclockwise, okay, as shown by the red arrow. So then, now this is a little bit of a tricky part that you might have problems with, so you just need to think it through. So I've got this represented as 180 degrees minus the inverse tan of 5 over 5, okay? So I'm not using 5 over minus 5 because that's going to give me a funny result that I have to interpret. So this is something that you're probably going to have to figure out how to use your trig. So really what I'm saying here is I'm going around 180 degrees and then coming back 45 degrees, and that's what this this angle represents, okay? So you just have to make sure that you do your trig right. Okay. And then that reduces to the polar representation of the phasor voltage, which is 5 root 2 at an angle of 135 degrees. Okay. So in red I've written the polar form on the phasor diagram. So we have both the rectangular form and the polar form here. Okay. So now the trick is to interpret this result back into the time domain. So this part is actually very easy, and what we're doing is we write cosine, and then from the polar form of the phasor voltage, we're dropping that down. So that's basically the scaling factor for the cosine wave. Okay, and then we drop the phase angle, we add it to the argument for cosine, and then we have to get the omega, and that came from the original problem. Okay, so that omega came from here. So up here, that's the omega, that's the 100. Okay, that's a radian frequency. So that's where we got that omega from. So this is the final expression that we're looking for. That is the time domain expression for the inductor voltage.